Going to bring our second panel to the beginning. So our moderator for this panel is Jim Richmond, and this panel is talking about From Data to Knowledge, the Eco-Informatics Imperative. Jim.
Thanks, Kathy. The first conversation I remember having when I came to NCEAS was with Matt and Mark, and they sat me down and explained the importance of some sort of data management approach that would be good for both ecology and good for NCEAS. And their notion was that they couldn't do custom solutions for every group that came in. That didn't keep groups that came in from requesting custom solutions, but their goal was to do something more generic. This is one of those things, maybe a lot of things are like this in ecology, that's easy to be glib about and sort of imagine its importance, but it's very difficult to do. The ecological data is bedeviled by a high degree of heterogeneity and other features that make it difficult to deal with. It's not like GenBank data, it's not like astronomical data. Everything's different. And so Matt and Mark understood this and began a long process of developing technical solutions to open access to data, while recognizing that there are also important cultural and sociological issues that are important. Their efforts, particularly at a place like NCEAS, a synthesis center that serves a very broad community, have led to many advances, although I've yet to see the do what I mean key, which is, I think, what we all wanted to see. Here's my data and do what I mean. So we're still hoping for that. As befitting synthesis center, there have been a lot of amazing collaborations here. We heard about some of them this morning. Lots of scholars and other acronyms. But many of those people who participated in those are here today. We're going to hear from them. We've heard from some of them already. Our goal as a panel is to discuss some of the issues and solutions pertaining to eco-informatics and increased access to data. We'll each take about 5 to 7 minutes to talk about some specific issues, and we hope this will stimulate some discussion. That's what we're seeking here. We're also prepared to pepper each other with questions if things start to drag, but given the last panel, I don't think doesn't appear that's going to happen. We'd like to hear from you about pressing questions you have, issues that you have dealt with or imagine you might have to deal with when making your data more broadly available, and some of your experiences managing and sharing data. Our speakers today are experienced in sort of both ends of this issue. Bill Michener from University of New Mexico and Matt Jones from NCEAS have been working a long time on these issues and worked together over many years. Josh Tewksbury and Brian Inquist will be giving more of the scientist sort of user's perspective. And we're going to have Bill and Matt talk first, and then we'll stop and have some questions, and then follow up with the other two speakers, and I'll make a few comments at the end of that point as well. Bill?
Thanks, Jim. I wanted to start off with just a little philosophical context from my own perspective, and that is, one, I think we're entering a new era of science and scholarship, and I think there are a lot of paradigm changes that are accompanying this new era, or entry into this new era. First of all, I believe that we're now seeing the emergence of grand challenge questions really driving science in general. And this is exemplified in the NSF budget, where we see the bulk of the new funding going for things like clean energy research, science, engineering, and education for sustainability, and then finally cyber infrastructure for the 21st century. The second paradigm shift that I think we're seeing as well is that data, for the first time in decades, with a couple of exceptions, including LTER and NCEAS, and again, a couple other that we can probably think of, data are now being viewed as valuable products of the scientific enterprise. And historically, a lot of projects, at the end of the day, you simply report the number of graduate students you supported, the number of publications, and that determined the success of your project. Now, increasingly, it's with requirements for data management plans from NSF, NIH, and other agencies, there's clearly a recognition that data are important, and they need to be preserved, and there needs to be a plan for doing so. Third, Organizational, as well as research networks and others, but particularly libraries, are now becoming the repositories for data and information. And this follows on a multi-century tradition of retaining books and journal articles and so on as their primary sources of knowledge. But again, the whole library culture is really changing dramatically. We're seeing that quite extensively across the world, as a matter of fact. Fourth, many of you may have heard of this, and I think this may be self-evident as well, and that is that data-intensive science is following Jim Gray's terminology, who was formerly with Microsoft Research before his untimely death off the coast here, argued that we were entering this fourth paradigm that followed on the heels of experimentation and observation on one hand, theory on the second, and then computer simulation on the third. And data-intensive science now allows us to ingest data and sort of do dynamic updates of models on the fly, so to speak. So it's really changing the way that science can be done. Finally, the fifth paradigm shift I think that's important is that data management, or eco-informatics as we now like to call it, has become the new statistics. And a lot of us in this room, when we went through school, that was like the one course we were required to take outside of our department was one or two statistics courses. Now I think in order to do the types of science that we're looking at via grand challenge questions and so on, they require us to deal with voluminous amounts of complex data. And there needs to be really training focused on that to meet the needs of students for, again, dealing with these large and complex databases. NCEAS, I would argue, has played an important role in helping us enter into this new era. And it's done through several areas, but three I want to focus on. One we especially heard about in the last panel, which was breaking down, I think, a lot of artificial barriers that existed at the time among departments, among universities, among disciplines, and so on. And NCEAS really helped bring people together from all of these different locations and mindsets. And a lot of, I don't know about you all, but a lot of the workshops that I was, working groups that I was a part of, usually the first half day or so was simply spent getting everyone speaking the same language. So I think that was really an important intermingling of different fields that took place there. And that led to new types of syntheses as well as meta-analysis and so on. And we weren't allowed to show graphics here, but I did a text mining analysis myself just prior to this. And it was really interesting to look at the trends between the terms meta-analysis, NCEAS, metadata, and biocomplexity. And they all showed pretty much the same trend, increasing over time. And I think that's really one of the outcomes as well. Another key area that NCEAS played a big role in was developing data, metadata management systems like EML, Ecological Metadata Language, Metacat, and Morpho that enable data to be documented, preserved, and shared. And this was highlighted also in the last session. And then third, I think another key area was exposing scientists and training postdocs in state-of-the-art informatics approaches, including tools like Kepler and so on, which folks here at NCEAS played a big role in helping to develop. There are some challenges ahead. The most important one, I think, is making it easier to discover and use data regardless of where it is and what format it's in. And NCEAS is helping to contribute to this, one via its participation in a project called Data One. This project is building a global federation of data repositories that makes it easy to discover the data wherever they may reside worldwide, and then also providing a toolkit that makes it that's quite closely integrated with the data. So a scientist can use a tool that they're familiar with, like Metacat, R, etc., and then tie the link to that and grab data from Data One resources again, and these will be globally. And this is meant to facilitate further synthesis. Second one is efforts by Mark Schildauer and others to support the development of semantic mediation tools that ultimately will make it much easier to integrate data sets, which I would argue is probably one of our biggest challenges, synthesis. And then finally, I think the one key area where we see major need for development is in the area of developing new visualization approaches, and I would argue that we need to go even broader by bringing in arts, the cognitive sciences, and informaticians and others in order to develop these solutions that will better enable us to visualize and interpret complex data sets.
Thanks, Bill. Matt, you want to follow?
Yeah, sure. Thank you. So NCEAS had the fortunate advantage of being founded right in 1994, 1995, in that period of time when the web was also coming of age. And it's really interesting, in 1994, as NCEAS was being evaluated and formed, there were only 623 websites in existence at that point in time. The following year, in 1995, there were over 10,000 websites. And so we really had the advantage of being able to ride a wave of internet growth that was phenomenal, and it changed the nature of, I think, interaction and collaboration and information sharing throughout society. But ecology and NCEAS in particular, I think, really benefited from that. When we started, it was clear that this technology atmosphere was going to be enabling, and our job was really to convince the community that we needed to be going down that road. And synthesis was a major driver for that. The nature of synthesis was a really exposed kind of an interesting conundrum, and especially in the early years. The people that are coming to NCEAS really were coming to consume data. They were people that wanted to reuse and synthesize data. And those same people were also field ecologists. They were at home producing data. And when they were playing those two different roles, they had two very different hats on. And sometimes it was hard to get people to realize that in order for them to synthesize data that somebody else was using, they've got to give up and share their own data. And that was an interesting transition. You could have people that were really playing both sides of that coin. We knew that in order to make these changes, it would be a long-term initiative. I mean, because NCEAS was a synthesis center that wasn't collecting its own data, our job was principally to convince the broader ecological community that they needed to create a data resource that could be mined for synthetic activities. And that was challenging. There would be technological issues that we needed to solve, but the principal issues were largely cultural and sort of community development. In addition, because NCEAS was formed and sort of conceived kind of before the internet really came about, a lot of the funding that you would have needed for these kinds of initiatives wasn't included in the original proposal. Unlike some of the more recent centers like NCEAS and NCEAS, that where informatics and outreach and data sharing were part and parcel of the call, that really wasn't true when NCEAS was called. And so we've had to build a program where we try to fund the informatics portion of the program separately from the core synthesis activities. And I think that's been a challenge that now is a lot easier, and I think it's easy to see how now there are opportunities for centers to build informatics right into the discipline, where when we started at NCEAS, that really wasn't part of the culture. So when we started putting together projects for NCEAS, there were really three different barriers that we saw as through the first several working groups. In 1996 and 1997, we kept having people come to NCEAS, they were bringing in their data, and they'd show up and they're hoping to get started on those really cool synthetic analyses on day one and day two. And like Kay said, day three, reality hits in, and you realize that, okay, a year from now, we're actually going to do analyses, because we're going to spend the next year compiling data. And we're going to spend a bunch of time cleansing data and figuring out, you have these taxonomic names, and I don't use those names. And so it's really interesting, because every project that came in had these same similar problems, but every one of them had their own custom sort of idiosyncrasies that they had to deal with. And so like Jim said, Mark and I said early on, we need to come up with a way that's scalable, that can really serve the needs of the broader community, and yet let groups continue on. And thus, the eco-informatics program at NCEAS was started largely to try to solve these larger scale issues that individual projects couldn't tackle on their own. So there's really three different areas that we felt we needed to focus on. The first was, as I mentioned, data sharing. There really was no major corpus of data available for synthesis groups. When we started, there were a few initiatives like the NDII that had begun, but they hadn't really gained a lot of traction yet. I think at this point now we've built a lot of data warehousing solutions like VegBank and PaleoDB and the interactions database, and we've also worked on the more generic data collections activities like the knowledge network for biocomplexity and other things. Okay. And those were great activities, but we're still working on building that critical mass of data that can be used for synthesis. It's interesting, although we've built now a data repository that has, say, 25,000 different data sets, we still find that when a synthesis working group comes, the data that they're interested in aren't yet there. So I think we've really not hit that critical mass where synthetic projects have a federated data repository. And that's what Phil alluded to, what the goals of this Data One project that are continuing this on are really meant to address. With Data One, we're hoping that instead of building a single data repository that can house all of the data that's necessary for synthetic and integrative studies, instead we build a federation of many hundreds or thousands of data repositories that are interoperable in ways that makes it so that it doesn't matter whether you put your data into an LTR system or you put it into the Oak Ridge DAC system or you put it into some other system. Regardless of where a scientist contributes their data, it's accessible to all the other scientists. And I think that will be a major move forward. So although we don't have the critical mass of data, at this point I kind of feel like we've achieved the activation energy that was really necessary to get the community into the mindset that they had to share data. So when we started, people were not of the mindset that they should share data. And now I really don't think, I rarely encounter anybody that says it's a bad idea for people to share the products of their research. In comparison, there are some other areas that I think are much more challenging. And the data sharing stuff I think is going to continue to gain momentum, but there are other aspects of synthesis that are really difficult. So for example, in addition to dealing with all those heterogeneous data sets, there are also lots of different analytical and modeling techniques. The types of syntheses that were conducted at NCEAS are really complex from a quantitative and computational perspective. And it's very difficult to communicate across, say, different disciplines, whether or not the methodologies that one group is using are the same or even different, because oftentimes they use different terminologies, they use different software systems. And so we've spent a fair amount of time focusing on how you can build analytical systems that can be used to document complex processes like syntheses. And so our work on scientific workflows and other kinds of activities like that are all focused on how you can build analytical systems that capture complex processes like synthesis. Okay. And the final area is semantics. I think that right now the major, that's a really good one. Semantics of data are still largely unclear in the ecological community. And I think when you start to do synthetic projects where you're trying to understand somebody else's data, it becomes inherently, very quickly obvious that you don't really understand what those methodological differences in data collection, what those will have, what kind of impact they'll have on the synthesis study you're going to do. So I think that's probably one of the major frontiers of informatics for the future, is how to take good descriptions of data sets, heterogeneous data sets that are inputs to synthesis activities, and make sure that we can scale up that process of data integration for synthesis. Thanks.
That's great. Thanks, Bill and Matt. We're incredibly fortunate to have people like Bill and Matt, because they're technologically adept. They kind of get it philosophically, and they understand the importance to our discipline and to science in general. Just a quick little story about Matt. When I first got here, he was helping the office staff set up the computers, and they came in as a group and said, "Oh, Matt's amazing. He just got in there and set everything up, and he was so nice. He didn't talk down to us." And then that same week, the LTR data managers were meeting at NCEAS, and they all came, 3 or 4 of them came into my office at the break and said, "Oh, Matt is so great. He just came in here and got everything working, and he doesn't talk down to us." He's so nice. That's, boy, you don't see that very often. The skills that Bill and Matt have. Let's go ahead and open it up for some comments and questions. Bob.
Thanks. This is Bob Pete. I've had the pleasure of being and the leadership role of a number of different cyber infrastructure projects which have come through NCEAS. And I wanted to reflect a little bit on my experience because I think there are some benefits we've gained from NCEAS that haven't really been clearly articulated yet. So we know a lot about the sort of academic and intellectual environment and how that has helped us here. And certainly it has helped with infrastructure when we've had working groups that get together here, are funded by NCEAS, and come up with good ideas about what to do, what we need. But then what? Well, you go talk to NSF and you get $1 million and you're going to build it. But how do you build it? Where do you build it? What are the problems? What do you do with it? So we have a problem as we look forward as to what we're going to be doing with this. One of the things we've had here at NCEAS is we've had a staff of people who are really knowledgeable about the methods, the cyber infrastructure approaches, the skills. So if you hire someone to work with you on an NSF project and put them here with this group, then they can interact with all the other skill sets and greatly benefit the project in a way that would not happen if it were done in your lab or maybe even just your university somewhere. In addition to that, there's a certain fragility when you hire one person to do a project. What happens if they fall off their surfboard and have a problem, or they get hired away by some highfalutin industry somewhere that can pay a lot more? Suddenly you've lost all of the knowledge and backgrounds. You lose 6 months of work. And when you lose 6 months of work getting back up to speed with your next hire, that's not good for your NSF project. But if you're working at a place like NCEAS where there's overlap in skills and background, there will be at least a significant amount of institutional memory about how it works and the knowledge necessary to make it work. So it really has been wonderful to be building these things here at NCEAS and benefiting from these. And at the same time being able to have the subject matter people come together and work here with it. Okay, so once you get it built, then what? You've got to maintain it. And that's even more challenging because you can't go knock on an SF door and say, I need money to keep this going in perpetuity, because that just doesn't fly. They want you to archive your data, but they don't tell you how to archive your products that are needing to be maintained. So when we build things here at NCEAS, we sometimes have the ability to simply have the staff here get a little bit of funding from us, or maybe not much at all, to keep the servers going, to upgrade the infrastructure that's needed to drive it. So that has been really critical. And when it breaks, there's somebody here who can go in and fix it and make it work. So with just a little bit of financial contribution, we've been able to keep things going for a decade. So that's been really important. And then the third thing is what happens as we move forward. We need upgrades, and it's tough to tell NSF we need a pile of money to do better what we've already done. So that's a challenge. So we're running some things here with software that's 10 years old, and believe it or not, software has changed in the last 10 years. And some of the code needs to be refactored to fit in with modern software. And gee, how do we do that? And the discipline has been evolving. So the data models behind that need to go into some of the database systems are now different. And our work here has resulted in at least several different international data exchange standards, all of which will be integrated into our systems. But we need to figure out a way to do that. And now there are new opportunities to integrate our products with new things that are out there. So all of this is coming along. And we've had some success at being able to do it here at NCEAS by having a critical mass of activities and having new projects which are somewhat different but yet can exploit what's been done. So I see things that we built 10 years ago now being improved, being marginally related to new things we have going on at NCEAS because of the critical mass. I don't know how I could do that at my home institution. So I'm trying to envision how we can keep the cyber infrastructure creation, maintenance, and updating going without an institution like this. Thanks.
I'm going to make Bob an honorary panelist. Bob has been involved in this, as he knows, for a long time, and his illustrations are always welcome. Other questions, comments? And then Nancy after that.
Lou Gross from Nimbus. Bill mentioned one of the challenges of education and training associated with data-intensive science. And I think looking at the potential opportunities for the future of NCEAS or what it might turn into, I think that's a major challenge. No one has a good idea as to how you effectively educate the variety of scientists from varieties of disciplines, not just ecology, on the modeling parts of it that Matt talked about as well, that we're not there yet in terms of knowing how much of what someone needs to know. We tried a number of things at Nimbus, and we're nowhere near as effective as we should be, particularly on the high-performance computing end. And the language that one needs to develop is voluminous, and so we've sort of come down to sort of building for our postdocs a sort of basic set of concepts, of the key ideas from these different fields, so at least you know the language. But beyond that, I don't know how to do it, and I think that offers lots of opportunities.
I would agree with that. One of the things we're doing in Data One is we're developing and providing learning modules related to all aspects of the data lifecycle. And I think those could easily and should be incorporated into every basic biology 101 or ecology 101 course. Secondly, I think because NSF is funding lots of larger projects now, like macrosystems biology and so on and so forth, there's a recognition that like LTER sites, there can be a great benefit in terms of hiring an eco-informatician or a data scientist or whatever to be on that project to help out with a lot of those various issues that you raised. So I think, that's going to be part of this new era is going to be the incorporation of data scientists into our research teams, because the grand challenge questions we're addressing are, it's a team sport. It's not something that one or two individuals could do.
Nancy?
Nancy Grimm. Yeah. So I wondered if you could address the question of the push-pull with respect to affecting a sea change in how the science uses data, explores data. We've been talking this morning about how NCEAS has had a really major role in that. But I also see that there are a number of things, for instance, NSF now requiring a data management plan for every proposal, journals starting to require or at least request that there be some kind of access to the data sets used, publication data sets and so forth. And I think probably the most important pull is really, I don't know if this is a push or a pull actually, but really the folks that we're going to hear from in a minute, I mean people who have actually been trained to make and incorporate as part of their research the use of data. But there's a lot of stuff going on, and also now working with the National Climate Assessment, I see the tremendous need for communication across federal agencies in addition to academic scientists, NGOs, and various other kinds of things. So could you just sort of speak about what you think some of the factors are that are driving, pushing this kind of transformation and pulling that kind of transformation?
Yeah.
So first, earlier people were talking about, saying, are the changes that we're seeing due to, say, impacts of NCEAS or any particular institution, or are we just following along with trends that, more generally have been in society? And I think that's part of it, is that, we've been seeing, like I said, this growth in the internet and the effectiveness of the internet throughout every aspect of society. And so some of those changes that you mentioned, are natural. They're happening in every field, right now. On the other hand, I think that there are very specific activities that have been undertaken over the years that have pushed our discipline forward, and sometimes faster than other disciplines. So Jim helped organize a series of workshops with Cliff Duke at ESA to really get 16 of the major ecological and evolutionary societies thinking about data sharing. And that series of workshops, I think, is what ultimately led to those journal requirements that are emerging today. And so, those workshops happened in 2001 or something like that, in that period. And so those things that you start then, those seeds that were planted then are now, blossoming. And you see data repositories like Dryad that I think are a direct result of those evangelism activities that Bill and Jim and other people in the community have really undertaken. And so I don't think it's an accident that NSF data management plans are being developed now. I think that those things are the direct result of informatics activities that have occurred over the years. Simultaneously with that, I think we also are riding this wave of more interaction and internet growth that's been going on.
I think of it as push-pull is a good way to think about it. We're going to be pushed by funding agencies or journals to do it, or we're going to be pulled by the opportunities developed by people like these. But I guess to put that together, it's these coalescing communities of interest, and you can see this happen with the work that Bill and Matt have done, where these bubbles grow and they start to intersect with adjacent disciplines, or they borrow capabilities from adjacent disciplines. And my sense is that's the way a lot of this is going to go. It's not going to be, just to plug this community into this community, or this bubble into this bubble. They're going to grow, intersect in some operationally important way at a synthesis center, or because a hot topic emerges, and then they'll figure out a way to do those things together. Dave, and then back there.
Dave Tillman. From early in my career, I not only generated data, but used OP data, other people's data, right? Going back to some data from the 1860s and at Rothamsted, England, and so on. And I'm very concerned about not just the data sharing aspect, which I don't think we're not over the hump on that one yet. We really have a lot of people who fear that if they share their data, they won't get the credit for what they've done. And there have been lots of people who use other people's data and never even cited the people they came from. I mean, that happens a lot. But I think even more seriously is that the data that people gathered 10, 20, 30 years ago in their career that they still are using will be very valuable, maybe more valuable 10, 20, 50, or 100 years in the future. Because the world is changing in lots of ways, and these old data can give incredible insights into what those changes are. And one of my concerns is, with your idea, Matt, of a distributed data network, is who's going to be in charge of archiving? Who will take over when NCEAS doesn't have money? What will happen to all those data? What will happen when any other place that is storing data no longer has funding to keep that going? And who will transfer the data from one kind of database to another kind of database and update the metadata and so on? We have to have it institutionalized in our science in some way. I really think we have to have one NSF-funded center that is in charge of all these data. And I really don't believe that we can afford the instability of having lots of distributed sort of coalition of lots of new sites. I'd love your thoughts on that.
Yeah, that's a fascinating comment, because it is the polar opposite of the design that we have undertaken for Data One. We thought a lot about this centralized versus distributed model when we were putting together our model for Data One. And one of the things we recognize, I don't know, everybody probably here knows that the NBAI, which was a pretty major government initiative for preserving biological resources over probably the last 10 or 15 years, was defunded over less than a 6-month period. And so, in my perspective, government agencies are no more permanent than any other institution. So, having NSF fund something and saying, in 75 years, will the National Oceanographic Data Center or will one of these other centers still exist? I think that is an open question. And so there are alternative models, and one of them is this idea that lots of copies of something keeps it safe, right? So there's this idea that if you build a distributed set of networks and make sure that data are replicated across institutionally diverse repositories, so that those different institutions are being supported under different funding models. Some of them are university libraries, some of them are government agencies, some of them are university labs, some of them are research networks like LTR. If you have that diversity of funding and purpose, and you can distribute the responsibility across that group, you're actually in a much better long-term position than you are depending upon any one centrally funded institution. And so that's part of the philosophy behind Data One. We do want to support large-scale data archives. We do want, to encourage the NASA DACs and those sorts of groups to exist, but we don't want to rely upon any one of those because we know that they have a lot of fragility in their persistence.
Moreover, the questions that a lot of us in the audience are asking are not U.S.-centric. They're truly global, and ecology doesn't stop at borders. So one of the issues that we address in Data One is we make it possible for groups in, let's say, Australia, Europe, Asia, and elsewhere to maintain their own repositories there, but then join this federation so that they can share their data and make it available to address global questions. And that's something that I think is really key as well.
Let's take one more question and then let Brian and Josh talk back there.
Alan Rodrigo, Nescent. So I actually have a question for Matt, because I was fascinated by something that you said, Matt, which was this idea of a congruence between pipelines of different projects, right? This idea that different projects may use equivalent analytic methods that are implicitly equivalent, but they are hard to detect, where it's hard to detect that equivalence. And I think this really speaks to the idea of synthesis at an even higher level than just the synthesis that's going on in the projects themselves. And I'm really intrigued to know how you would navigate that and how you negotiate that and how you recognize that. I think that is such a fundamental question from the informatics perspective that I would love to know, how it can be done.
Yeah, I can't actually say that I know how you would recognize those sorts of equivalences, but what we have recognized is that although we've spent a fair amount of time focusing on the importance of documenting data and its importance for synthesis, what we haven't spent nearly as much time on as a community is documenting the analytical and modeling procedures in ways that, well, in a couple of ways. One, so that somebody else can just understand what you did, but in another, so that somebody else can reuse what you did. And so efforts like Kepler and the workflow systems and systems like CRAN and R, I think are great ways to move forward with building reusable analytical systems where you don't have to recognize that two modeling components are the same because the two people actually use the same modeling component. Whereas right now, I think in the ecological and environmental sciences community, there's a lot of reinventing the same analytical wheels. And so I think if we can get past that, you don't have to recognize those similarities as much as you do now.
Right.
Great. Thanks, Jim. Thanks, everybody. So Jim called me up and asked me if I wanted to sit on the eco-informatics panel here. And my first reaction is that, well, I'm not an informatician. But he's like, no. You're actually doing informatics. And I'm like, well, no, not really. I know a lot of informaticians, and they've influenced me quite a bit. But Jim was really interested in kind of the boots on the ground kind of viewpoint. And actually first came to NCEAS, I was part of the third wave of postdocs, 1999 and 2000. Part of a working group actually led by Felicia Smith, having to do with body size and ecology and evolution. And part of that working group were mashing together a lot of data, basically what most working groups do, right? Mashing together data and coming up with a lot of hacks with, in terms of the solutions of how to integrate all these different data and then to address the different questions that we're interested in. And so then over the years I've returned to NCEAS, part of different working groups, very similar, approaches to meshing together all these different data. And then more recently, I've been leading a working group together with Bob Peet, Mark, and Rick Condit, and Brad Boyle. Both of them are not here, unfortunately. But what we've been trying to do is integrate all botanical data that we can find for the Americas. And so this is ecological plot data, herbarium data, trait data. We're like, okay, there's going to be some issues, but how do we put all of these together? And so we've actually learned quite a few things. And one of the first things I learned was that when I first met Mark, I sat in a room with Mark. I was writing a lot of notes, and then a few other postdocs and I, we went out of the room and we're like, did you understand what he said? I was like, what are these terms, what are these words? And so we compiled our Rosetta Stone of acronyms for informatics. And Mark, you are now known as, in postdoc world, as acronym man. So, but once I learned how to understand Mark, things got much better, from there. But I have to say, both Jim Riggins, Matt, Mark have influenced me quite a bit. So in terms of what are the central kind of informatics issues that we've had to deal with, I just wanted to make 5 points. A few of these points have already been made, okay? So you can see this as kind of underscoring. And I'm making these 5 points with the viewpoint of NCEAS 2.0, okay? So how do we move forward from here? A lot of these points have been kind of echoed and reiterated by others, so I'm seeing kind of a consensus in things. And so I think the first point that I want to make is that in these various working groups, when we get together, we mash together all these data, do these analyses. About 6 months down the road, I asked someone who did, part of the analysis or even my own analysis with the various data. We go back and we write the methods like, well, how did you do that? Like, well, I did this and that, and then we go back and try to redo it, and you get a different result. And so I can't underscore the importance of trying to formalize the creation of repeatable workflows and having a way to formalize that, a way to publish workflows. Okay. So as scientists, we have to be very concerned because science needs to be repeatable. And the one thing that I think I've learned in these working groups is that often we can't repeat some of the analyses that we do because there's several steps in scrubbing, cleaning, meshing together various different data, right? And so I think everybody has had this feeling. And so we do a lot of data massaging and whatever to pull together this data. And so we need to have publishable workflows, right? So you can go to the original data sources and then recreate exactly what was done. The second is this issue of data provenance. And I mention this only because I've now learned that not all data, even though the units are the same, okay, not all data are created equal. Right? There are different methods involved in putting together the different data that we use, coming from different people. Statistically, we could analyze the data that came from Jim Brown as being slightly different than the data that came from Jamie Galuli, for example. Not singling you out or anything, but there's an issue of how then we actually go, even though they were supposed to do the same thing, how then actually were these data collected. So the importance of having the associated metadata to give more of a deeper understanding of what those data mean. All right? So just because the units are the same doesn't mean necessarily that the data are equal. Lastly, actually the third point, and David Tillman just mentioned this, is the issue of data sharing. And I think we've come a long way and we've made a lot of great advances in data sharing and the culture of data sharing. And a lot of our data are much more public than they used to be. But when I talk to my colleagues at the University of Arizona that are genomicists, and I see all their big data that they're creating, and then I look at all of our big data, there's actually a very big difference between kind of this bioinformatics genomics data and our data. A lot of blood, sweat, and tears goes into our data, right? And so people are hesitant still, okay, to share their data. And so I think the NCEAS model of bringing people together still has an incredibly useful role of actually pressing the flesh, getting to know somebody that you've read in the literature, and trusting them that, yes, I can share my data. So even though we've made great advances, I think in ecology in particular, this is still a very central and important issue. And so for NCEAS 2.0, I think we still have a lot to learn from the original NCEAS model. And so copying that, I think, would be a very good thing. The fourth point that I wanted to make is, and I have to say that, in looking out in the audience here, I don't really see too many taxonomists. And in meshing together all of our data, one of the biggest scares that I had was we're trying to compare species diversity between two sites. And we couldn't do that because there is a fundamental problem in terms of how we apply names to things. And Bob Pete has been kind of pressing me over the years, and I now see the light. I think the issue of names is probably the most fundamental issue kind of facing us in terms of integrating our biological data, okay? So whenever you pull together different data sets, everything hangs on a name, okay? Names change, there's synonymies, and it turns out we're really bad spellers. And so we've been trying to create tools that actually correct data. And one fact that I will throw out is that on average, 30% of all of your data are wrong in terms of your names, including mine, which was a very big kind of insight. And my last point that I want to make, and I can make this very quickly, is that I think the pace at which we utilize informatics and in terms of how informatics can be useful is that it needs to be driven by science, in particular both applied and pure questions, okay? And I think what we found in our working groups in particular is that if we had specific scientific questions and we could sit down with people who understood some of these informatics issues, we would make great progress, okay? And that often resulted in novel tools and things that were useful in terms of creating reliable workflows and repeatable workflows. Okay, so I'll stop with that.
Great, thanks, Brian. Josh?
All right, so I could just sort of say what he said, because that was great. I think Brian and I come from some similar perspectives on some of these things. Folks who are much more end users than creators of eco-informatics. And I'll just try and reiterate some of those points, add a couple others, take it for a little bit more of a sort of outside perspective of how the field of ecology appears to be changing, and sort of some of the the pressures on our field coming from outside the field, from society at large. When we're the age of biology running into the information economy, what we value changes. So in the information ecology, the data is our currency, and those disciplines that are able to provide data to complex environmental problems in a timely fashion are going to drive the debate. And I think we want to be there driving that debate, but I don't think we always are because of some of the issues that are being discussed today. We can do a better job of that, and I think eco-informatics is one of the key tools to getting us there. So I started thinking about, well, what are the aspects of our data we're looking for? Predictive and prescriptive ecology is where a lot of us are going. In order to create and maximize that, we have to have it both scalable and portable. So we're looking for portable knowledge, we're looking for knowledge that scales well, and this is about providing relevant data. A lot of our data is fantastic, but at the wrong scale, and this is about creating the right names and the right scaling factors, and doing more than just collaborating, but actually getting together and to create best practice standards for the data that we actually collect. And lastly, of course, the accessibility and transparency, compatible with knowledge generated in other fields. So, when I've been sort of reflecting on this, it's a great time to be an ecologist because our field has never had a greater spotlight placed on it than it is right now from outside. But when I look around, I see the norms changing really fast, and a lot of questions come into my mind about how we actually train the next generation and how we retool and retrain ourselves with these norms that are changing so fast. And eco-informatics for me is one place I look to try and find solutions to those rapidly changing norms. As the questions become more and more complex and the answers that are demanded are at scales that are larger and larger, and also with finer and finer grain, the way in which I collect my data is no longer appropriate or sufficient to answer those questions, and it really calls into question sort of the way in which we think about our field. So, in some ways, we're maybe moving from a one investigator, one system, small grant, dark data sort of focus of ecology into something that's much more broadly collaborative, where innovation comes from our capacity to work collectively, to articulate and adhere to sort of commonly agreed upon best practices, and to think a little bit more about what we do that not just serves our publication needs, but also serves the society that needs ecologists who are playing well with others. And I'm going to return to that point a little bit, this idea of what NCEAS and institutions like it are doing to allow us to play well with others. And I think everyone has touched on that as being a central role that NCEAS has played. And we've also talked a lot about what's come out of that kind of work. And the outgrowth, the nutrient network, the trait net, the National Phenology Network, the team project. The list goes on. And for me, NCEAS is sort of not only a part of all those, but it's a place where it had this amazing ability to sort of create common ground between a wide range of topics. This idea that we didn't constrain it to this type of science or that type of science, but we could have user-inspired science mixing with stuff that has this mostly basic understanding in a somewhat inspired link between data and theory. It was this organic, inspired linkage that I think made it a very safe place to do almost any type of ecology. And my experience here was primarily as a sabbatical person and coming in, doing something really different than what I'd done before, or really what even an NCEAS had done. And there was a very accepting atmosphere to a different kind of, to a very different kind of science. So I think one of the things that two or three other points. One is that one of the things that I'm struggling with is how does this transformation take place so that when we move forward, we're retaining what I think is great about our small science, I'll call it, culture, which is the individual creativity and the sort of access to your own data that comes from people being intimately involved in single investigator work, and how do you keep some of that creativity as you move into these broader collaborations where necessarily you're going to have a lot more management structure between one level and another of these broad data collection networks. How do you retain that? I think that's something that the next synthesis centers will have to be struggling with. And I think I'm still here. Okay, so I have too much to say. The other thing that I think others have talked about a little bit is sort of how these kind of synthesis centers and how the next NCEAS 2.0 helps us move to what an open ecology framework could look like. How do we sort of cross these bridges that Brian was talking about provenance, so that we establish a standard data provenance that allows us to value different parts of our contribution. Because 2 minutes left. One of the things that I think we often forget is that there's a lot of institutional barriers to making these change happen that are outside of NCEAS's purview. And so what we value in promotion and tenure is pretty narrow at this point. And until that changes, it's going to be very hard for the society to get beyond its current place. I think a lot of people are working very hard within the constraints that are placed upon us. But those constraints are sort of, we need to challenge those more effectively, I think, as a society. And I want to talk just about two other issues. There's one thing we haven't talked much about is the importance of eco-informatics in sort of what is commonly called citizen science. So, there are approximately 25,000 practicing ecologists in the world, and there's probably 10 to 20 million species in the world, and a lot more interactions. So the idea that this group, ecologists, professional ecologists, are going to be in charge of gathering and curating and disseminating the information on the natural world is ludicrous at some level. And what has to happen is sort of a transformation in which we question who is a part of science. Maybe science is a lot more like civics for a lot of people, where a lot more people are doing a little of it, and then the professional ecologists are helping to collect and orchestrate that collection so it's actually usable. That kind of a change is happening. And I think these kind of centers are tremendous places where we can direct that change. And eco-informatics is sort of the language that will be necessary to make that an effective change. And then one thing that just came up, we were talking about training. However we do this, we have to be a little bit careful when we talk about what we want, all the new skill sets that we're asking the next generation to have as ecologists. Because one question I don't see asked very much is, what don't you want them to learn right now? And so, because I think that's an equally important question, and there's some obvious answers, but I think we're adding more than we're taking away. And if one thing that comes out of this is that we have this abundant need for empirical information about our planet. And we don't get that just from learning new eco-informatics tools. We also need to sustain the practice of the collection of that information, which isn't near as sort of next generation. We've been doing that for years and years and years. But it's still an important part of sort of how we build this collaborative network, where we retain that knowledge and add on this new generation of eco-informatics people that will help me make my change. I think that's all I have to say.
I think you're right.
Excellent.
All right, let's take some questions and comments here, and then Bob. Kristen?
My name's Steve Kelling. In the work that we do, a lot of the analyses that the analysts talk about work on this ratio of 80% of their time is really dealing with organizing the data. And then it's 20% of the time actually doing the analysis. So when we explore that and find out what are those issues and the kinds of modeling and analysis that we do, species distribution modeling stuff, we find that access to data is actually fairly straightforward. You can go to a NASA DAC or NOAA and pull down data sets that you can then attempt to link to your data. But that while the semantic issues are really important, there's huge syntactic challenges that we face, and a researcher faces, as they try to navigate how you access these different kinds of data sources from these different kinds of repositories. So I think that's that data interoperability challenge, it's not only the semantic component, which you guys really well define here, but the syntactic issues about differences in how each data repository holds these data is a huge challenge. And then once we do get the data together, and once we go through that 80% time in pulling all of this data together, what we found out, which surprised the hell out of us, was that the volume of data that the model results generated were orders of magnitude greater than the raw data that we put into the model. So that brings up a whole new challenge of visualization of data, exploration of data, tools that can be open to and accessible to a researcher to allow them to see if there are patterns after these huge analyses occur. And then the issue of storing and maintaining and versioning all of the second generational data, the model results data, is a huge challenge in the future. I know that Matt and Bill and I talked about this quite a bit, but I wonder if you guys, the two of you, on the researcher's side, have any comments about that?
Yeah, so quickly, I couldn't agree with you more. It's this 80% of the time in terms of what you're doing with the data to scrub it and standardize it and get it into R or something to do your analyses. That, I think, is really the rate limiting step. And to be just a little bit provocative here, I think the NCEAS informatics team has developed these amazing tools like Kepler and Morpho and so on. But when the rubber hits the road, it's almost as if we need more basic tools of integration and this learning of how we can use these more general kind of informatics tools in these specific problems. And so I think we actually have quite a bit more work to do in terms of that 80% of the time, developing tools that really help us solve that part. And I think there's some general things that we all do. Now, in our group, we focused on one of them, and that's taxonomic standardization, which, by the way, you can all use now. It's called the TNRS, or the Taxonomic Name Resolution Service. We just put it out. It's freely available on the web. It'll scrub all your botanical data. And that, for us, that has cut down probably 50% of the time in terms of integrating. But there's still a lot to do.
That's great. Thanks for bringing those up. I think if Bob could get a microphone, I think he was next, and then after that, back there.
Yes, I have two things I wanted to discuss. I'm Bob Wade. I'm from the LTR Network Office. Brian, you mentioned that you thought that informatics needed to be science-driven. And I hear this an awful lot from people who are doing research, and I think at some level it's absolutely true.
I think to be useful, it needs to be science-driven.
However, that contrasts a little bit with the way Matt started off his comments about not being able to design custom approaches for every kind of issue. So I wondered if there is a real kind of point of discussion there that you guys want to elaborate on a little bit, because the point of archiving data is to be used over and over and over again to address different kinds of questions. So I don't see how informatics structures can focus on specifics on it.
So I actually don't think there's a conflict between what Brian and I said. And I think there are generic tools that can be used for multiple different science-driven cases. And the Taxonomic Name Resolution Service is a fantastic example. We've been calling, Bob Pete made me aware of this issue back when he first started trying to propose working on benchmark, that this issue of the changes in taxonomic names and their relationship to species concepts is fundamental to any kind of integrative synthetic biological study, and yet it's like the elephant in the room. Nobody ever deals with it. And so finding a generic solution to that has been on our radar for informatics for well over a decade. And finally, there's solutions that are starting to emerge with things like TNRS. And we're still not there, but that's the kind of solution that I think that can be applied to any science-driven use case that's out there. Like, there are very few studies that have gone through NCEAS that couldn't benefit from the ability to quickly, resolve the taxonomic ambiguities among multiple input data sets that are going into the synthesis.
So just to follow up, one of the differences, I think, with the SEEK project, which was a precursor to Data One that NCEAS and LTR and others were involved in, one of the things that set those two projects apart, and one of the reasons that I think NSF views them as so successful, is they're all based on science drivers. And we have, for example, under Data One, we have a group that Steve Kelling and Bob Cook are in charge of called Exploration, Visualization, and Analysis. And this group focuses on a different science question that is extremely complex, involves lots of different disciplines and scientists, and that helps drive informatics developments from that particular perspective. So it started out in ecological niche modeling, and then it went to now as part of the next climate change assessment report, and so on and so forth. So that information from the scientific community is what's really driving informatics solutions we're developing. And this is opposed to a lot of other projects funded in NSF by OCI and SIDES that are funded strictly for informatics' sake or computer science's sake.
I have a second thing, and it's very short. And that is, I was in a meeting last week at the Metric Scale Ecology meeting. And I had the opportunity to take a quick poll among the people there for the 20 different projects. And I asked them how many of them were confident that they knew how they were going to manage their data from their projects. And fully expecting them all to raise their hands, because they all had data management plans in their proposals. And 3 people out of 80 raised their hands. And it makes me feel somewhat less confident that our community is really ready to take advantage of these tools, and perhaps there's an opportunity for NCEAS and other people to address these kinds of issues too.
That's a good point.
Is this on? Okay, great. This is Jai Ranganathan. I'm here at NCEAS. I just reflect a bit on something that Josh, you posed, which is what about citizen science and how does that impact ecoinformatics? And I'm thinking about things like the iNaturalist, a phone app, just something that some people at Stanford are putting together, which is where it's revolutionizing who's collecting ecological data. It's actual people, just regular people with this iPhone app collecting unbelievable species records from all over the place. And how do things like that sort of connect into sort of these traditional methods of ecoinformatics, where this is just, we're always talking about ecoinformatics being hard enough among scientists. When you start adding in all these additional repositories of data, the challenge seems really hard.
That's a great question. I mean, one of the things that immediately comes to mind is that they have been, that particular group has been working on some of the similar problems that Brian's been working on taxonomy, and they have a relatively good and quickly evolving sort of system for helping the lay users through this problem of identification. I mean, the whole idea of crowdsourcing some of our work is something that has only been made possible in recent times, and it's something that I think is inevitably going to take a larger and larger chunk out of what we think of as science, as we are able to take advantage of sort of the human data networks, the hyper-distributed data collection possibility of the fact of 1 in 4 people are going to have a smartphone by 20 years, and things like that that are changing the way in which we do things at vast scales. And it's already being used in many countries with text messaging, and you don't need a smartphone to do a lot of this work. And I would say that in some of those networks have been developed by the NGO community who wants answers and don't have the manpower to do it. But there haven't been sort of a standardized framework. Like, for example, iNaturalist doesn't have a plan on how to deal with its data either. And it has a lot of data, and it's only scratching the surface. And neither does iSpot has a little bit better one, but not great. And Project NOAA is in the same place. None of them know exactly what to do with all the information they're collecting. And they probably could use a lot more guidance from the scientific community on how to become bigger players in this process. So there's a huge opportunity there. I don't think that a lot of professional scientists are using that opportunity or engaging sufficiently with that rise to be able to sort of influence the decision at this point. It's inevitably going to change, and the faster we get involved, I think the better.
That's good. Let's take one more comment and then try to wrap it up. Let's go back here.
Mark Cadat. This is interesting because I think that people are really talking about two levels. One is sort of this philosophical idea about how to share data, and the other is more pragmatic. And it seems like the pragmatic part is where we're stuck. And I was interested that it was mentioned about genomics data. And I'm someone that uses GenBank. And to me, it's not that there's a philosophical difference. It's that their data is so ubiquitous and so
Much more easier to obtain.
well, not only that, but yeah, but it's standardized in how they do it. It's not to say there aren't errors and whatnot, but it is really standardized. And I know that when I go on and I get genetic data, I'm not concerned about how they got it because we have A's, T's, C's, and G's. But so I think what people keep revolving around is this pragmatic issue of you get this data and you don't know how different people collect the data. Is it the same thing? I mean, there have been some calls for standardized data, like how to measure plant traits and stuff like that. And so the question, basically, to me, is not how we get data together, but how do we get people, scientists, there's 25,000 ecologists, how do we get them on board using certain types of methods, certain types of routines, so that we can ensure that the data coming in is collected in similar ways. And I think that to me, that's the limiting effect.
No, I agree with that completely. And you mentioned the trait people. So if you go into TraitNet, Try, they're all associated with this network of plant functional traits, and they have handbooks for how you measure all of these different traits. And there's going to be a revision of that. So there's a new one coming out. And so I think that's a shining example of the community coming together and agreeing on standardized protocols for how you measure things. And now in the journals, if you don't follow those protocols, then there's a very good chance that paper will not be accepted or the data will be heavily questioned.
I think that's a strong argument. I think we're never going to obviously catch up with GenBank in that regard because we're measuring more than those 4 letters. But anyway, I have about 7 minutes of things to talk about, but I will make it to 2 minutes. Let me just say that one notion of NCEAS 2.0 could be parallel to Science 2.0. And this is the basic idea of using very large amounts of data and massive collaboration. It's obviously more another thing that's easy to be glib about, but difficult to pull off. But there are things we've talked about here that are not even being addressed. Not only are they difficult, but they're just kind of out there that are difficult to address, just like using common methods and so forth. The other thing is, in our discipline especially, is the sociological and cultural aspects of what we do. How do we get people to share data? How about changing the reward system in a way that these things can happen? And I can imagine in NCEAS 2.0 that focused on those not just interdisciplinary, but in the interstices of how we do what we do, in the spaces in between, where unless it's forced, they're essentially never going to be colliding disciplines that require some sort of cooperation and collaboration. They're things that are just the way we behave. If we make this international, it becomes even more complex. The different cultures see collaboration and sharing and rewards in very different ways. So I think if we start to look at the notion of Science 2.0 and imagine that NCEAS 2.0 or some other entity is going to be working in the cracks, working in places where nobody's going to go unless it's forced, as opposed to imagining that over time, these interdisciplinary, cross-disciplinary activities are going to take place as the interests of two parties or two entities start to collide. So we'll just leave it there and get some lunch and hope that we have continuing conversations at that point.